We wanted to show that the integers together with a smaller equal is actually a poset. So every integer is smaller or equal than itself. So it is reflexive. If a is smaller than b and b smaller or equal than b and b is smaller equal than a, then a has to be. So it is antisymmetric. And if a is smaller than b and b is smaller than c, then also a is smaller than c. So it is also transitive. So we just showed that this is a poset. Z together with smaller equal is a poset. Okay. So Yesim, can you tell us if Z plus, so these are the positive integers, together with the divisibility relation, is it this a poset?
I guess so. I think it's poset.
But can you, we have to prove it, right? We have 3 properties to prove. Shall we go through this? So is the relation reflexive? Yes, Sim? So if we take an element, does it divide itself?
Yes, it's reflexive.
Is it antisymmetric?
Yes.
Why? So if A divides B and B divides A, then A has to be equal to B, right? So, and it is transitive because if A divides B and B divides C, then also A divides C. So if this was written, you will have to give a bit more details on why this is true. But in general, I think we all accept it, right? So is the last one a poset? Sefa. Omer Farouk. Okay, the last one is also a poset. It's one of the most famous posets, actually. So the power set of a set S together with set inclusion, so the subset relation, this is a poset because every set is a subset of itself. If A is a subset of B and B is a subset of A, then A is equal to B. This was a definition of equality of sets. And if A is included in B and B is included in C, then A is also included in C. We can see this very easily from the Venn diagram, for example. So these are posets. Are there questions about the definition of poset? You have to ask questions if you don't understand. And also, if you cannot hear me, you have to tell me. There is no way for me to know that you cannot hear me. Kadir, is there a question? Okay. So let's say we have 2 elements, A and B, in a poset, A with some order relation, right? Then these 2 elements are called comparable if either A is smaller than B or B is smaller than A. By the way, when I have an order relation, I usually say smaller or less, or greater or the other direction, right? So A is less than B or B is less than A. If any of the 2 happens, then they are called comparable. We can compare them. If none of this happens, then they're not comparable. They're incomparable. Okay. So, yes.
In case of equality, sir.
Well, we don't care. We care if we can compare them. If the pair AB or the pair BA is in the in the relation. So if A is equal to B, then since the relation has to be reflexive, then it will be comparable. Both A and AA, they're there, right? So every element is comparable to itself because this is one of the prerequisites for having an order relation. Does this answer the question?
Actually, no.
So
what is the correct mean of this sign? I mean, A plus B.
I mean, this is any order relation. It's not plus. It's some relation.
Relation.
You can think of it as subset or as
okay.
less equal.
All right.
So
Okay.
any order relation. I'm using on purpose different signs. So in the previous slide, I used this and that and that. These are three different order relations. But the only thing we require is that it satisfies the three conditions, that it's reflexive, antisymmetric, and transitive. It doesn't matter what sign you use, right? So questions. In the poset, we saw that this is a poset, right? Z with smaller equal, are 3 and 9 comparable? Metehan. Hussein. Merve. Hussein, Omer.
Yes, sir.
Are they comparable?
Can you ask me again?
In the poset of the integers with smaller equal, are 3 and 9 comparable?
Yes.
Okay. Berkan, in the same poset, are 3 and 5 comparable? Buket?
Yes.
They are comparable.
Yes.
And what about the next question? In the poset of positive integers with divisibility, are 3 and 9 comparable?
I think yes, because 3 divides 9.
Good. So 3 is smaller than 9 in this relation, right? So we
Yes.
can compare them.
Yes.
And thank you. Janer, in the poset of positive integers with divisibility, are 3 and 5 comparable?
I think yes, teacher.
Why?
Because 3 is smaller than 5.
What does it mean? Is it smaller than 5? 3 is smaller than 5?
Yes, and it is changed.
I don't think so.
What?
3 is not smaller than 5. Because what is smaller?
It change for operation. That not.
So 3 is not divided 5, so it's not smaller.
I don't know what is it.
The word smaller you use, it refers to some order relation, right? So if you want to say that something is smaller than something else, you have to. And here, smaller means that, right? Is this clear to everyone? So
I think we should consider only the sign operation, right? Is it less than or divisible or any other signs? We should focus on the sign to be able to decide this is
not the sign, the relation. I may say R there. I give you a relation. I give you a subset of the Cartesian product. Any order relation. If I give you an order relation, what is smaller, right? It is 3 and 5 is only smaller if the pair 3, 5 belongs to the subset that defines, right? And 3, 5 does not belong because 3 does not divide 5. Also, 5 does not divide 3. So these are not comparable. Is it better now?
Yes, sir. Thank you.
So
It's
when
clear.
we say comparable, we always mean with respect to the relation, to the order relation we have for the poset, right? As we say here. This is why I didn't put anything. I put a generic sign, a generic symbol. So any order relation of the poset. Okay.
Can I ask a question?
Yes.
About previous slide? If there was not Z but R rational numbers,
Okay.
would it be comparable?
For the last one, yes, because everything divides everything else. So this is a trivial relation, right? Since everything
Yes.
divides everything else except for 0, then all elements are comparable. But
Okay.
the relation contains every pair, right?
Yes.
Okay. So it's impossible to find everything is comparable because everything is smaller than anything else, and so smaller than 5 and 5 is smaller than 3 there with respect to the relation you say. Okay. Because 5 divides 3 in the rational numbers. So, by the way, what I'm saying is not 100% correct because this kind of divisibility, it means that I mean, it's only divided over integers because we want the remainder to be an integer. But if you consider it over rationals, divisibility doesn't mean anything. Everything divides everything else. Okay. Now, what is the total order? A or linear ordered set. Later we'll understand why this is linear. And the relation is called the total order or a linear order. We also call it a chain if it is totally ordered. So questions: is the poset, is the integers together with smaller equal a totally ordered set? Well, since I say example, yes, it is, because every 2 elements you can compare them. It's either smaller or bigger or equal. So, but in this example, in the poset of positive integers with divisibility, we saw that so 3 and 5, for example, are not comparable. So it is not a total order. Total order just means that you cannot find 2 elements that are not comparable. Okay. Now, if we have a poset, we call it well ordered if this relation is a total order. And every non-empty subset has a least element. So if we take A, then it has a smallest element. This example, sorry. So this should be Z. I take the Cartesian product and I order it by lexicographic ordering. So lexicographic ordering means that is smaller than, so you have a pair, right? A, B, and you want to compare it with C, D. If A is smaller than C, then the first pair is smaller than the second. But if they're equal, one. It's the same order that you have in encyclopedias, etc. So you none of ever used a physical dictionary or this is how dictionaries used to be. They're sorted. So
Sorry, you still have some
seen
problems with your voice.
So have you seen a physical dictionary in your life? Have you ever used such a thing? Can you hear me now? Is it better?
I guess it's better.
I didn't understand the last 2 minutes.
So the lexicographic ordering, so here I said this is Z times Z. So how do we compare two pairs? Let's say we have AB, one pair, and another pair CD. So AB is smaller than CD if A is smaller than C, or if A is equal to C and B is smaller than D. So in this case, and this is how we used to sort words in dictionaries, which in Greek is called lexicon. This is why it's called lexicographic, the ordering. So this lex I put here, this is for lexicographic. Here, is this poset, why this is not well ordered? Can you hear me?
Yes.
Okay. So then I will ask Dan Berg why this poset is not well ordered. Elif Nur.
Sir.
Why is this poset not well ordered?
Sir, I don't understand what is the lex.
So lexicographic means, so if you have two pairs, let's say the first pair is A comma B and the second is C comma D, and we want to compare these pairs. So here there is a Z missing, right? This is a Cartesian product of Z with Z. So we want to compare the two pairs. How do we compare them? We say that the first pair is smaller than the second pair if A is smaller than C, or if A is equal to C, then if B is smaller than D. So if the first elements are equal, then we compare the second. But the first one get priority. So if the first two, if from the first elements we can decide what is bigger or smaller, we do. If they're equal, we go to the next one. So this is how you search things, you sort things alphabetically, right? In a letter, you sort the words first according to the first letter, then according to the second, etc. This is why it's called lexicography. Is it better now?
Yes, I understand, sir.
But now my question is about the second one. So why this poset is not well ordered? Enis. Fatih Khan. Kahraman Arda. Kamil Jihan. Mete. Merve.
Because it is, for example, it is 9 and 3. If it is 9 and 3, then it is not sufficient for well-ordered sets. 9 greater than 3. But it is 3 and 4. If it is 3 and 4, then it's sufficient for well-ordered sets.
But wait. So here what we say is that the definition is a bit more complicated. This is why I wanted to discuss this a bit more. This is important for induction, by the way. So here the definition says that every non-empty subset of A has a least element. So in the two sets, you pick a subset with two elements, right? And 3, 9, well, 3 is the least element, is smaller than 9, right? So it doesn't contradict well-orderedness. We have to find a subset, a non-empty subset. And there is no element that is smaller than the others, than all the others. Is this better now? Rian, you wanted something?
I will try to answer. judging on your previous example. Well, maybe that's because if we have two subsets A and B and C and D, without legs, we will compare A and D and C and B, and that's wrong, maybe.
But now this is a new poset. This is just the integers. So the thing here is, can I take a subset of the integers that does not have a smallest element? If you take actually any infinite set that goes up to towards minus infinity, let's say take all the negative numbers, okay? All the negative numbers are integers, right? It's a subset of the integers, but there is no element in the integers that is smaller than all others. Do we agree? If you tell me that minus 1 trillion is the smallest element, no, I can find minus 1 trillion 1, which is smaller.
So, sir, I think we can say for the second one, we cannot guarantee it to select any subset is ordered one.
No, so to be well ordered, it means that every subset must have a list element.
Yeah, for example, the first one is ordered according to lexicography, right? That's why we can say this is a poset. This is already ordered according to lexicography ordering,
Okay, but
right?
the second is also ordered according to smaller equal.
But if we
So
choose any subset randomly, for example, -1 and 2, or 2 and -1.
This is ordered. Okay, but
so
they're ordered.
So we must obey this rule, the less than rule.
Yes.
So
and there is a smallest. In all the examples you gave, there is a smallest element. There is a least element. If you take a set of two elements, since this is a total order,
okay,
one of them will be smaller. They are comparable, right? So all elements are comparable because this is a total order. So if you have a finite subset, it will have a least element. So the examples you gave are not counter examples for this, because if they are finite, then there will be a least element. It has a least element. We actually need an infinite set. So, and I'm suggesting, for example, the negative integers. The negative integers do not have a least element. There is no element. You cannot say this. Then they have a small element, right?
Right.
And this is.
Can I ask something? Can you explain what is the Cartesian again?
So within itself, there is a Z missing there. So, but actually, this example, I want you to check if it is well ordered as an exercise. I said it is well ordered, but you shouldn't believe me. You should check it. Okay? I believe now it is not well ordered. So I hope it's confusing enough to make you do the exercise. It's not hard. Yes.
That's actually very confusing.
Yeah. So I was wrong. Here, this is. I believe this is not well ordered. But if it is well ordered, you have to tell me why. I'm telling you why this is not well ordered. This is not well ordered because if you go to the negative numbers, there is no smallest. Take all the negative numbers, then there is no smallest element of this set. If you take all the positive numbers, no negative numbers, then there is a least element. And this is how we do induction. So for induction, we need a well-ordered set. This is why we do induction over the non-negative integers or positive integers and not over the integers in general. But there was a question. No question?
So are we comparing Z and Z relation Z in the first example? Should we compare Z plus relation Z plus for a very ordered set?
So here, if it is Z plus, then it is well ordered. Yes.
Okay.
Okay. So are there other questions? No. Okay. Now, how do we want to see, to visualize partially ordered sets? So we take the graph of the relation, the directed graph. So the elements are the nodes, the points, and then we draw an arrow if an element is related to another. So if we have a pair A, B, we draw an arrow from A to B. Okay? But then we have to remove some arrow. Since every order relation is, we will have loops. Every element will have an arrow to itself. We don't need this. We know if it's an order relation, this would be there anyway. They don't give us any information. It's also transitive. So if we have an arrow from A to B and an arrow from B to C, we also have an arrow from A to C. But we don't need this A to C because obviously if A goes to B and B to C, then also because of transitivity, A has to go to C. And usually we draw things by taking arrows going upwards. So here's examples. If we take the poset 1, 3, 4 with a smaller equal, then this is the graph. So 3 is smaller than 4, 2 is smaller than 4, 1 is smaller than 4, 2 is smaller than 2, okay? But let's remove the loops. We remove these 4 loops, and now we remove the transitivity relations, and we have this, which is much easier to read, right? So here what it means is 1 is smaller than 2, 2 smaller than 3, 3 is smaller than 4. And I think this is much better to understand what's going on. So, and this is why it's called the chain. Remember when we said that this is that a total order is called the chain? That's why. So, any question about how to draw the Hasse diagram? This is called the Hasse diagram of the relation of this poset. The Hasse diagram of the poset. Okay. No questions? Perfect.
Sir, I understand this diagram because, sir, I can see before diagram, Hasse diagram. Can I see? Because I have a question.
Okay.
Why arrow don't go from 1 to 2? I don't understand.
We go from 1 to 2.
Yes,
1
sir.
is smaller than 2. Right?
Yes, I don't understand. Yes.
1 is smaller than 2, so we connect 1 to 2. This represents this relation. So we connect elements if they are in this relation. So 1 is smaller than 2, so the pair 1, 2 is in the relation. So we put an arrow from 1 to 2. Is it clear now?
Yes, sir. Thank you.
But then we remove the things that do not offer more information because we know that every element will be related to itself. We don't have to put an arrow because in bigger sets, this will be unreadable. For example, here, where we have 1, 2, 3, 4, 6, 8, 12 by divisibility. So 1 divides everything, right? 1 goes everywhere. So 2 divides 4, divides 8, divides 6 and 12, but it doesn't divide 2 and 3. 4 divides 12 and 8, right? So then we remove the loops. and then we remove the transitivity. So for example, 3 divides 6, 6 divides 12. We don't need an arrow from 3 to 12, so we remove it. And we have this nice diagram telling us what our relation is essentially. So 1 divides 3, so 1 divides everything that's above it, so everything. 2 divides everything that is above, so 6, 4, 6, 8, 12, etc. Do you see how it works? So this is the Hasse diagram for this poset. Okay. And some elements in the poset are a bit special. For example, an element A is called maximal if there is no other element that is larger than that. So then it's called maximal. It is called minimal if there is no other element that is smaller than that. It is the greatest if for all other elements A is bigger than this, and least if it is smaller than all other elements. So I used this notation to make clear because this may be confusing, right? So what is maximal? Maximal, it means that there is no other bigger, but greatest is a very different thing. It means that it's greater than everything else. Here, this does not mean that it's greater than everything else. It's possible that it's incomparable, for example. Here, for example, who can tell me what poset is this? Which poset is this?
Is it subset?
It is a subset of the set ABC, right?
Yes.
So, and the relation is a subset inclusion. So in this poset, is AB a maximal element?
No.
Why?
Because ABC is bigger than AB.
Exactly. So there is a B such that it's bigger than the element A. What are the maximal elements in this poset? Raise your hands. You have 1 minute. Raise your hands.
Can you repeat the question?
What are the maximal elements of this poset? By the way, you can prepare also the minimal because that's what I will ask next, right? Rian. Is there a question or you want to give the answer?
Did you call me, sir?
Someone wanted to raise their hands.
Can I answer?
Rian? Yes.
AC, ABC, BC.
So you say ABC is maximal, AC is maximal.
BC, yeah.
Why not AB?
Because ABC is bigger than AB.
Is it also bigger than AC?
What?
ABC is also bigger than AC, right?
Like yes.
So for the same reason, AC is also not maximal.
Yes, only ABC then.
ABC. And what is the minimal?
Could be A. No, empty. Only empty because they are
Only
bigger than empty. The rest of them bigger than empty.
Okay, who is answering?
Sir.
Yes.
How do we compare these letters? According to what? According to their positions or their lexicography, ordering?
So this is subset. So this is a set, and this is a subset of that set, right?
The set is ABC, and all the others are the subset of the ABCs.
Exactly.
Okay. So how can we say the A is less than B or B is less than C? According to what?
They are not. So they are not comparable. The set A and the set C are not comparable.
Yeah. So how can we figure out, how can we find the maximal or minimal if we cannot compare?
So let's check if A is maximal.
Okay.
Is there an element B?
Yes.
Such that B is greater than A? Yes. AC, for example. By the way, these A's and B's are not the same as these.
Okay.
Our set now is the power set. So these are subsets.
So any power set is greater than a subset.
Any set is greater than its subset. This is the definition according to this is the order we have, right? So this is why the empty set is smaller than anything, because it's included in every other set. And ABC includes all other subsets.
Okay. So the minimal is empty set and the maximal is ABC.
Exactly.
Yeah. Okay.
In this case, it's also the greatest element, right? ABC is the greatest because for all other sets, ABC contains every other set. And also the empty set is the least element because it is contained in every other set. Okay. So this relation here now for this example is inclusion. Now let's see the example on the right. Ali, do you want to give me the maximal elements? Rian?
Maximal elements are 12, 20, and 25.
12, 20, and 25. That's right. Nothing is larger than this, right? So we have 3 maximal elements. Here we only had 1, but as you can see, we can have more than 1 maximal element. Bouquet, can you give me the minimal elements?
2 and 5.
2 and 5. Nothing is smaller than 2. Nothing is smaller than 5. Satai, can you give me the greatest element?
The greatest element. Do we again follow the tree structure or?
For this one.
For second one.
Yes.
Greatest. We count all the elements, right? It's not we are following a tree structure. Then it's 25.
There is no structure. So these are just, we mean that 2 is smaller than 10, 2 is smaller than 4. We don't even care what it means. We have a diagram, so we know the relation. We don't have to interpret what it means.
So, okay, then 25. If we are counting
10.
No,
why 25 is larger than 10?
Well, it's the all-holder set. It's the bigger.
How is it bigger?
Elements.
No, we cannot compare 10 and 25.
Oh,
25 is definitely not bigger than 10.
Hold on a second, Greens.
Also, 10 is not bigger than 25. But 25 is not bigger than 10 as well. None of them is bigger than the other.
Then we can go to 20.
20?
The biggest, maybe the
Yeah,
biggest.
why 20 and not 12?
Well, it's bigger. If we follow from the 4 nodes, maybe it is the bigger than the 12.
Why?
I don't actually understand the relation though, how we compare this. I don't exactly follow that, but
if it is higher, it is bigger. This is the definition. If there is an edge going upwards from 4 to 12, this means 12 is larger than 4.
okay. So there is no other comparison. We just follow upwards. That's it.
Yes.
That's all we
yes.
do.
This is how we draw the diagram, right?
Oh, okay. Then it's just 20 and 12. The two upper.
Well, yeah, but not. Why not 25 then?
It's on the lower, maybe.
No. So the point is, the greatest element if all other elements are smaller than that. Do we have such an element? So if you say, if you say 12, 20 is not smaller. So 12 is not the greatest. If you say 20, 12 is not smaller. So 20 is not the greatest. If you say 25, 20 is not smaller. So 25 is not the greatest. So we don't have a greatest element. There is no reason why we should have a greatest element in a poset. We also do not have a least element here because 2 and 5 are minimal, but none of them is smaller than the other. So there is nothing, no single element such that all others are smaller. Right?
Okay.
So there should be a line between the two elements, right? There should be a relation directly to be able to comparable.
I mean, there is the relation. Here, you see the relation here.
Okay, you said 2 and 5 are not comparable.
Yes.
The reason is there is not a line, direct line between. Okay, it's clear now.
By the way, if you think a bit, you can see what is the relation behind this, right? What is the logic? I assume this is divisibility, but we don't care. If I give you the Hasse diagram, this is your relation. This gives you everything you need to know. So 2 is smaller than 10, 2 is smaller than 4, etc. But 2 and 5 are not comparable. 4, 10, and 25 are not comparable. 12 and 25 are not. 12 and 10 are not. Okay? 2 and 25 are not comparable because there is no line. Yes.
If we had an arrows between, I mean, 2 to 10, there is an arrow, and 10 to 5, there was an arrow. So we can say 2 and 5 has a relation, right?
No. They don't. The fact that they are both, they are smaller than 10. Okay, we know this.
Yeah.
So what do we need to be greatest element is the one that upper bound has connected to every single?
Yes. So no, not necessarily. But it has to be that there is no element greater. Yes.
Hello?
Yes. It has to be above everything else, right?
Yes.
Yeah.
It has to be one. Sorry. So it has bounds with every single item, or just
like here, ABC is the greatest element.
Yes.
Yeah.
Okay. Then so it doesn't actually need bound with the C elements, but it is somehow connected with other subnodes as well. So it is the greatest element.
It is the greatest element, and it is connected with everything because of transitivity.
Oh, I see. I see. Thank you, sir. Okay.
Okay. So now let's go for bounds. Let's say that we have a subset of our set A, where A is a poset according to this relation. Now, an upper bound U is an element of A such that all elements of B are smaller than U. And a lower bound is an element of A such that all elements of B are smaller than B. So remember, here you have to see that upper and lower bounds refer to a subset, refer to a set. So all elements of this set must be smaller or greater. And then we call them upper bound and lower bound of B. Okay? So, and what is very interesting, important, is the least upper bound and the greatest lower bound. So the least upper bound of B is an upper bound of B such that there is no, such that it's the least among all the upper bounds. We may have many upper bounds, right, for a set B. The smallest of them, the least among all the upper bounds, is called the lower upper bound. Sorry, the least upper bound. Now, if we take all the lower bounds and we take the greatest among all these, then it's the greatest lower bound. Okay. Let's go to these examples. If B is the set D, F, E, what is the greatest, the least upper bound? Burcu. Emirhan. Fatih. Hayrettin Kasim. Muhammad Iqbal.
Yes, sir.
Someone? Yes.
I don't understand clearly. I read it the screen. I don't understand clearly.
Okay, so let's see. I asked, we have D, E, and F, and we want to find the least upper bound. So what are the upper bounds for D, E, and F? Is there an element that is an upper bound for D, E, F? F, exactly, and it's the only one, right?
Yes.
So it is the least upper bound. Sorry, is it the only one?
For DEF, I think yes.
What about J?
J is bigger than F.
Also than D and E, right? It's
yes.
larger than all. And what about H?
H is equal to J.
No, it's not equal. They're not comparable. But it's greater than D, it's greater than E, it's greater than F. So H, J, and F are all upper bounds, right?
Yes, but these two are
larger than. So the least upper bound is F, as you said. Can you hear me?
My voice was closed. H and J are same height.
It doesn't matter. The point is that they are not comparable.
I understand.
So F is the least upper bound because it's smaller than H and smaller than J, these are all the upper bounds, and F is the smallest among them. So it is the least among upper bounds of B. Right? Thank you, George. And if we take B, C, D, E, Metehan, what is the greatest and the least upper bound and the greatest lower bound? Usmane? Muslim? Seval? Sefa? Umit? Yusuf?
Yes, sir.
What was the question?
Yeah. Me or the other Yusuf?
Whoever wants to answer.
Okay. Let me try to answer.
The question.
But you said the upper bound and the greatest lower bound for the second part.
Yes.
For which, what is the starting point?
So the set B is BCED.
BCED. For BCED, the lower bound is A, and the greatest lower bound is also A.
So B is not a lower bound for BCD?
Actually, it's also a lower bound. So that is the greatest one also.
So B is the greatest lower bound, right?
Yeah.
And the least upper bound?
And the least upper bound is A. What was the letter order? E. E. Yeah, that is E.
I agree. So now let's go back. No, back. And I have a question. If our relation is divisibility, what is the least upper bound? Let's take two elements. So I give you, we have a set, right? And I give you B to be the set, a pair, A and B, two elements of our set.
Okay.
And I'm asking you about the least upper bound of these two elements. And our poset is according to divisibility. You can think of it as this one. This is according to divisibility. This is the set 2, 4, 5, 10, 12, 20, 25, according to divisibility.
Okay.
If I give you two elements, and I ask you what is the least upper bound, what does it mean? What is this least upper bound? Does it have a meaning?
According to the relation.
Yes, of course.
Yeah. So that means the upper bound number that can be divisible.
Okay. Do we have a name for
divisible number? It's multiples of the smaller number.
You're almost there. So how do we call the smallest number that is a multiple of two others? It is the least.
Yeah.
Least common multiple, right?
Yeah.
So it's the least common multiple. And what about the greatest lower bound?
So it is the maximum, not least.
This also has a good name. Yes, the greatest.
The greatest multiples
No,
of
it divides now, right?
Yeah.
So this now divides the other two numbers.
Okay.
So it's greatest something
Greatest
divisor.
Denominator.
Divisor.
Divisor.
Says GCD. It's the greatest common divisor, right?
Yeah. Common divisor.
So you will have divisibility. So I just wanted to show you that these things actually have a meaning. So the least upper bound, the greatest least lower bound, they have meaning according to the relation, right? So, okay. And let's go for the last definition for today, and we are done. A partially ordered set in which every pair of elements has both a least upper bound and a greatest lower bound, it's called a lattice. So let's read it again. So we have a poset where every pair of elements has a least upper bound and a greatest lower bound. So, for example, here, is this a lattice?
Yes, it is. It has also least upper bound and greatest lower bounds, both.
Do we all agree? I leave this open. I will not answer this. You will do it as exercise. What about this one?
Only
Sorry?
A1. Sorry,
Yeah.
sir. I answer it for A.
I agree. For B, Yesim.
Yasin, you called, right?
Okay. But you answered the previous one.
Yes.
I said Yesim. I wanted to say Yesim, but I don't know what.
Okay, sorry, sir.
No problem. Ümit. Süleyman.
I don't know.
Serhat.
Sorry.
Süleyman, is B a poset? Sorry, a lattice.
I'm not sure about that. Probably yes, because there is D and F, but I don't know.
What does D and F mean? Sedef, Özlem, Ozan, Murat, Mete, Merve, Mehmet Selman, Kamil Zihan, Hüseyin, Hakan.
Hüseyin or Hüseyin Ömer?
Sorry?
Hüseyin or Hüseyin Ömer? Which one?
B.
So I guess it's you then, you should answer.
I thought B. But you can tell me for either of the two. Is B a lattice? Is C a lattice? Hakan?
I'm not sure, however, I would say no, because they're not, I mean, there are ones that I can't compare, right?
So
like I can't
what
compare
about
D and
C?
E.
So what about this one? About C?
That could be true, because I'm not really sure, sorry.
Okay, good. So then I think by now you are convinced that you have to check these three examples. It's not as simple as it looks. So for this you have to check it. But for these three, for these four, let's discuss it now. So let's say we have positive integers with divisibility. Is it a lattice or not?
Sir, we don't have any bound values. I mean, upper or
Why?
lower. Because we have all the positive
Of course
integers.
we do.
We cannot say which one is the greatest or which one is the least.
We can. So when we say greatest and least, you cannot. Here the relation is divisibility. It doesn't matter how big they are. If one divides the other, it's okay.
Oh yeah, okay. Yes.
So in order to prove that it's a lattice, we just need to know that every pair of elements has a least upper bound and a greatest lower bound. I actually gave you the answer earlier. Elif Nur.
Sir, which question?
If Z plus, so the positive integers with divisibility is a lattice.
I think it's a lattice. Maybe. I'm not sure, but
Okay.
It must be have a pair of elements because of the its infinite number.
Well, but the question is if there is a least upper bound and a greatest lower bound for every pair. So this.
I don't understand.
Right. Okay, we will discuss it. Ibrahim.
Bu videomuzda matematik
Kamil Zihan. Yes, so is it a lattice or not?
I really don't know, but I think it could be because everyone has least upper bound and greatest lower bound for if they can divide.
So I guess for the first one would be the greatest lower bound. So on that part, it could be correct. But if it goes to infinity, that can also divide. Well, we can't use it to divide, but that can be divided. Would that make it a least upper bound?
Infinity.
Yeah.
It's not in Z. The number infinity is not in this set. So it's infinite. So
Sir, may I put in something, a little thing here?
We said.
Hello?
Sir, your voice disappeared again.
Sir, we cannot hear you.
Sir, your mic is again cutting out on and off. Sir?
Sir, unfortunately, we cannot hear you.
Sorry, we cannot hear you. Are you connected?
Yes, he's here, but we can't hear.
İmece usulü yedirdik, içirdik. Dedik ki mahalleye, ülkeye bir faydası olsun, okuttuk hep beraber. Doğru. Kes. Hilmi'nin ona ihtiyacı yok. Gel gör ki koca üniversitede sadece okumuş musun oğlum? Ne kimseyle tanışmış, ne kimseye merhaba demişler. Bildiğin fidan girip sığır çıkmış fakülteden. Doğrudur. Doğru. Ne dedim ben? Ne dedim? İşini bilir. Fakülte birincisi. Muhasebe bunun işi. Hesap makinesi var kafasında. Sor bir soru. 100 lira kazan. 2 yıl vergi vermedi. Cezam kaç lira olur?
Hileli soru. 2 yılda bir af çıkar zaten.
Zehir mübarek zehir. Şimdi Hilmi.
We still cannot hear you.
Sen bu çocuğun elinden tutacaksın. Mahallenin zengini sensin. Doğru. Buna iş vereceksin. Anlıyorsun Hilmi.
Your icon is shining. Okay. Çıktı. Sanırım bir tanesini daha açacak ya da bitirecek.
Sürekli mikrofonda gidiyor ama.
Bu arada 19 kişi çıktı. 70 kişiydik.
Ama yeni bir şey açmadım.